Hey guys, welcome back. I hope you enjoyed your Christmas break. We do have a few announcements that I need to talk about. We will be continuing on with our cascading model. So if you're a B student, if you're on the B schedule, then you're going to be 2 days behind the A students, so that we're doing everything in person, the entire same thing the whole week. So this lesson will be done in person if you are meeting in person. If you're doing distance learning, you can go ahead and do this now anytime you want. It doesn't really matter. But I'm making the video primarily for those who are doing distance learning. So hi, unfortunately won't be able to see you guys the rest of the semester, but let me know if you need any help. I can still do private tutoring, stuff like that through Google Meets and stuff. So you're still my students, and I really wish you guys hopefully will be able to come back, but if not, it's good to have you. So let's talk about another thing, is that grades. So they extended the deadline for the grades for the first semester through the 22nd of January. So we've got about 3 more weeks left or whatever. A little less than 3 weeks, but you get the idea. But you have to turn in, so I'll let you turn in any missing work, but you have to give me enough time to grade it. So try to get it in before the 22nd of January. Keep in mind that the homework is 60% of your grade. So for every homework assignment you turn in, that's actually worth like 2% of your overall grade. So if you turn in 5 missing homework assignments completed, that'll raise your grade an entire letter grade. So from a C to a B, from B to an A. So definitely make sure you have all of your missing work turned in. And then the rest of your grades based on the test. And so if you still need help getting your grade up, just talk to me and we can do some tutoring and retake some tests. All right, so I think that's pretty much it. Welcome back. This cannot be worse than the first semester. That's not even possible. So I'm excited. I've got a lot of cool stuff planned. I've already planned out the rest of the semester because that's how I roll. And we're going to be able to do some fun in-class activities. I'm really looking forward to it, and it's only going to get better from here. So I'm feeling a lot better. It feels good to be back and back in the saddle and back in the swing of things. So let's get going. Polygons. So polygons means many sides, I believe. Yeah. So many and sides are actually angles. Yeah. So poly means many, and gons, I believe, is where we get angles from. So it means many angles. So a polygon is a closed geometric figure with 3 or more straight sides, but those sides also come along with angles. So if you look over here, this is a closed geometric figure. It has 3 or more straight sides, so this would be a polygon, and this is specifically called a pentagon because it has 5 sides. Over here, this would be a triangle, but it's open. It's not a closed figure, even though it does have straight sides. And the other question, so this would not be a polygon. I guess I could cross that one out here. And then the last one we have here is a circle. So a circle is a closed geometric figure with 3 or more straight sides. But the question is, are the sides here straight? We're going to get into that in the next slide. It's going to blow your mind, because I will say that this is a polygon, and it's, yeah, I'll give it a special name, but you might say, no, it has one side and it's a curved side that goes all the way around, but I don't know. I can think of it differently. All right, so is a circle a polygon? That's the question we're going to answer. So the first thing is we have polygon is 3 sides, which would be a triangle or trigon. Triangle. Anyway, a gon really just means angle. So triangle, trigon, that's what we're talking about. Anyway, 4 sides, we call that a quadrilateral. The lateral part means 4 sides, so not 4 angles, but that would be different. And then 5 sides would be a pentagon, which just means pent or 5 angles. And then 6 would be a hexagon. 7, you probably don't know this one. There's 2 names you can call it, either a heptagon, which is Greek, or a septagon, which is in Latin. I guess heptagon is more common, but you can call it septagon if you want. 8, everyone knows that one, octagon. 9 is a nonagon. You might not know that one. 10 is a decagon. I believe this is there's a name for this one, but you don't have to know it. We're just going to call it an 11gon, and if there's anyone that you don't know, you can pretty much just call an 11gon after 10, so it doesn't matter. 12 has names, dodecagons. I think this is undecagon. Yeah, so undecagon, dodecagon, tridecagon. Just kidding. Actually, it might have a name, but you don't have to know them. We'll just call it 13gon, 14gon, 15gon, 16gon. All right, so as we increase the number of sides, if you notice, the polygon starts to look a lot like a circle. In fact, if I showed you a synagon or a 100-sided polygon, you wouldn't even be able to see the flat sides. It would look just like a circle to me. So as we increase from 3 sides to a regular 100 gone, and if we do infinitely many sides, is that not going to turn into a circle? Like, wouldn't it like converge to a circle? So is a circle a polygon with infinitely many flat straight sides, right? So if we think about a circle is a collection of all equidistant points, and there's infinitely many points, even infinitely points that exist in between those 2 points, right? And then every 2 of those points, which are like infinitesimally like right next to each other, we connect a line of, a segment in between those 2 points, which would be a straight side. So, man, does your brain hurt? Because I'm digging this stuff. So anyway, I would say that it's actually, a circle is a polygon with infinitely many sides. So instead of one curved side, it actually has infinitely many straight sides to it. And I call it an infinigon. So I'm making up my own stuff at this point, I'm pretty sure. But that's okay. Good stuff. All right, so which polygon has more sides? So we've already established that a circle or an infinigon has infinitely many sides. So what happens when we cut one in half? All right, so now we're just dealing with this semicircle. Does it have more or less sides than the circle? All right, well, there are half as many, so it's half of infinite. So that was infinite divided by 2, but then we add this additional long side here, so it'll be plus 1. So how many sides? What is half of infinity? So half of infinity is actually still infinity. It's not affected by dividing it by 2, which is mind-blowing. And then if you add 1 to infinity, it's still infinity. It's not any bigger infinity than this infinity. There's really only 2 types of infinity, countable and uncountable. Yes, Canner. But anyway, good, awesome stuff. So which one has more sides? Neither. They actually have the same number of sides. A sphere and a hemisphere have the same number of sides if they are indeed polygons. They're both infinitely many sides, which blows minds. I'm having way too much fun, and we're only 7 minutes in. All right, so closed versus an open figure. So obviously this is a closed triangle. This is an open one. We can actually tell, we didn't get into this because we skipped a unit because we had to do compasses. We'll probably do it at the end of the year. But triangle inequality theorem, we can actually even tell kind of converse of Pythagorean theorem, stuff like that. But we can actually tell if this is going to make a triangle because the sides are 5 and 4, which adds up to 9, and 9 is not bigger than 10. So those 2 sides are going to be too short. They're not actually going to reach each other. So no matter how I swing the side lengths of 5 and 4, if the longest side is 10, they're going to be too short by 1, right? So this goes a distance of 5, that goes a distance of 4, but they're too short by 1. And it's not actually enough for them to both be equal to 10, to sum to 10, but they actually be bigger than 10 in order to make it into a triangle. Otherwise it would just be a flat line. Like here, 6 plus 6 is 12, and 12 is bigger than 10, so we're good to go. All right, so this is obviously a closed figure. This is a closed pentagon. Here we have a quadrilateral, but it's an open quadrilateral, so it's not actually a polygon, even though it has 4 sides. All right, so regular versus irregular. Which one would you say here would be a regular quadrilateral? So both of these are quadrilaterals. Both of these are pentagons. Which one is a regular quadrilateral and a regular pentagon? You're probably thinking the one on the left. Well, it looks regular, but how do we define what it means to be regular? Good question. Could it be by rotational symmetry? So with a regular polygon like this octagon here, it does actually have rotational symmetry. And that's actually the same thing we pointed out with objects that had rotational symmetry, is that we're able to rotate them less than 100 or less than 360 degrees, and it matches up on itself again. Now the reason for that is because we have 8 points here, just like a regular octagon. So if you notice, it matches up exactly there, which is lovely. And then the amount that we're rotating it, if we have 8 points, we just did 8 divided by 360, which would look here. So 360 degrees all the way around in our degree circle of oughtness, right? And then that divided by 8, which would leave us with 45 degrees, I believe. Yeah, 45 degrees. So every time we rotate the image 45 degrees, it will line up on itself again, which is kind of cool. So could we use that to define rotational symmetry, to define what it means to be regular? Well, the next part that I'll show you is, well, what about this the star here? This is actually a decagon because it's got 10 sides. It's got 5 points here though. So that kind of breaks our rule, doesn't it? But on this one, is it a regular shape? Well, if we define regular by meaning that all the sides are going to be the same, so like on this pentagon, all the lengths of the sides are the same, then that would actually hold for this this decagon over here as well, because all the sides are the same. But the difference, and where we're actually going to define what it means to be a regular or irregular polygon, is based on the angles. So the angles actually form the shape, not as much as the sides do, because we could have it concave or convex in this case, and still have the same sides, right? So each one of these angles alternates between being an acute angle and an obtuse angle, right? So if all the angles are the same, then it is a regular polygon. So on a square, all the angles are right angles, and so it's a regular quadrilateral. And on this pentagon, all the angles are the same, so this one would be a regular polygon. This one's actually irregular because the angles are not the same. Same thing over here. These are not all the same angles, so this would be irregular. Same with the pentagon down here. All right, so it's not enough just to have rotational symmetry. We have to have all the angles are the same. And if all the angles are the same, all the sides will actually have to be the same as well. There's a principle there, triangle inequality theorem going on. All right, so then concave versus convex. Concave means that it's caved in. So one of the ways you can see that is if you can connect 2 points here, and it's not going to cross the sides here, that means that the actual figure was caved in. Another way of looking at that is if you have an angle, an interior angle, that is more than 180 degrees, like we do here, then that would mean that it has to be concave. So you'll notice we don't have any interior angles. This is one of the interiors, this is another interior angle, this is another interior. None of our interior angles over here on this side are going to be more than 180 degrees, more than a straight angle. And that means that the shape itself has to be, lost my train of thought. It has to be convex. Yeah. All right. So convex is not caved in. Concave, just look at the word. Just remember cave, like caved in. Okay. So these are clearly caved in because we have more than 180 degrees. This one's also more than 180 degrees. And you can see, oh, look, it looks kind of like a cave. The figure's caved in, concave. All right. And another thing, by the way, if it's a regular polygon and all the angles have to be the same, well, all the angles can't be more than 180 degrees. And so regular polygons are always going to be convex. Kind of interesting. Classifying polygons. All right, we got 4 sides. So this is a quadrilateral. It's caved in because this angle, interior angle, is more than 180 degrees. So this would be a concave quadrilateral. Over here we have 1, 2, 3, 4, 5 sides. So it's actually a pentagon, even though it looks like the mountains. It's not. It's actually a pentagon. And it's caved in as well because, again, we have more than 180 degrees here. So this is it's a concave pentagon. All right, triangles, geometric figure with 3 sides, triangle, 3 angles, trigons, meh, whatever. All right, all of these have 3 sides, but there's more ways we can classify specifically these different, differentiating between these different triangles. So we can classify triangles by their angles and by their sides. So if we look at their angles, all these angles here are acute, so this would be an acute triangle. The angle here is obtuse because it's more than 180, so this would be an obtuse triangle. This has a right angle, so it's a right triangle, and this one has all 3 sides are the same, which means all the angles have to be the same as well, meaning this is equal angular. We can also call it equilateral, which is probably what you're used to, but equal angular refers to the same angles in the triangle. Equilateral would mean that the sides are the same, but they're actually the exact same triangle, so either way. Another thing that I want to point out here is that the smallest side is going to be opposite of the smallest angle. The biggest, longest side, in other words, is going to be opposite the biggest angle, and the medium side is opposite the middle angle as well. So if we look over here, our biggest angle is going to be opposite our longest side. And then if I ask between these 2 angles, B and C, which one is the smallest angle? Well, they actually kind of look kind of similar, but you can probably tell this one's smallest. The easiest way to answer the question is looking at the side. So the smallest side is AC, and so that would mean that the smallest angle is opposite of that, which is going to be B over here, and then the medium side is AB, so the medium angle is going to be angle C. All right, kind of cool. You can do the same thing over here. So smallest, smallest, biggest, biggest, medium, medium. Kind of cool. And the same thing applies here. So these 2 are both the smallest, meaning both of their angles are going to be equal, and that's the base angles of any isosceles triangle, right? Which is kind of cool. And if all 3 of the sides are equal, then all 3 of the angles have to be equal as well. This is called the triangle inequality theorem. All right, you also classify by the side. So scaling means all the sides are different. We mark those with different markings, so 1, 2, and 3, or whatever you want to do. Just make sure they're different. And then with the, so this would be called a scalene triangle. We could also call it a scalene acute triangle if we're going to classify it fully. Then over here we'd have an obtuse triangle, right? And then if we classify it by its sides, we know all the sides are different on this one. So this is obviously obtuse. That's not right. This would be obtuse scalene or scalene obtuse. I messed that up, didn't I? Yeah, that should be scalene obtuse. Fixed it. All right, then over here we have isosceles, right? It also has a right angle, so it would be an isosceles right triangle, and then equilateral, and then by the angles, equiangular. So you could call it either one. That actually implies, because they're an improper subset, if it's equilateral, it has to be equiangular as well. All right, isosceles triangles means that two sides are the same. If we look at a radius of a circle and then we move, these two sides are going to be the same, right? This radius is the same as that radius. Then if I move this point here, let's say I move it down to here, and then I connect this one over here. Notice with the red triangle, it's still isosceles because these are still both radiuses that are just in different locations. So now instead of an isosceles right triangle, like the blue triangle in the background, we now have the red triangle, which is an isosceles obtuse triangle. So the base angles of an isosceles triangle are going to be congruent. That's the base angles theorem. We can actually prove it a few ways, so let's do one of them. So here we notice the two sides are going to be congruent, so then we know the base angles are the same. All right, one way we can prove that is with the midpoint. So if I take the base and I find the midpoint, which means I cut it into two equal halves, and then I connect the apex to the midpoint, that's going to be this line here. Well, we know these two sides are the same, the hypotenuse is in this case. These two legs were split in half because it's the midpoint, by definition of a midpoint. And then also the side in the middle is reflexive. It's the same side for both triangles. So we know these two triangles are congruent by side, 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 side congruency postulate, which is what we did one of the last things. And then if they are congruent, then that means all their corresponding angles or all the other corresponding parts, CBC, TC, have to be congruent as well, meaning this angle down here is congruent to this base angle over here. Now another way we could have done this, let me back up quick, is that if we drop a perpendicular diagonal, so just go straight down and it will actually cut the angle in half here, then from that, we actually have enough information because the reflexive one in here, we have an angle side, side, a money sign, donkey postulate, right? But it's not the donkey postulate because we have a right angle. We actually call it the hypotenuse leg theorem because this side here, as I said, was the hypotenuse because it's opposite a right angle. And this would be one of the side lengths or one of the legs. So hypotenuse leg theorem. All right, so anyway, what you need to know is that the base angles, which would be this angle here and this angle here, have to be congruent because they're opposite congruent sides. And so if the sides are congruent, then their opposite angles are congruent as well. All right, equilateral triangles. This one's actually kind of fun with compasses. There's actually an equilateral triangle here. If I move this one up here, I'm guessing there, then you can possibly see the equilateral triangle. Can you see it now? All right, oops, that's not perfect. Okay, so how do we do it? With the magic of editing, boom, that's how you fix it. That was quite magical, honestly. How did I do that? How did I know to do that? Because I've been teaching geometry for a long time. But isn't it cool, like these secrets of the universe? Illuminati confirmed. All right, so why does this work? Well, we have the same circle. We started out with the same circle because they were coinciding, right? And then I move the midpoint to the other side of this radius. Well, we know the radius of both the circles are still the same. So where these two circles intersect, they're intersecting with this radius and this radius over here, and we already established that radius there, and so they have to be equilateral because they're all the same radius. Now we can do the exact same thing here, but with a compass, because compasses are making circles. But instead of making a full circle, we're just going to do an arc. So I'm going to go up from one side, and that's the set of all points that are equidistant from this one, or at least a part of it, an arc. Then I'm going to flip the compass to the other side. Isn't this awesome? And do the same thing here. It's the same distance. It's just going from the other direction. And then go up, and where that intersects, that has to be the location of the third point, which is like this third point you see here. And I can connect those if I want to. And there's my equilateral triangle. Boom, mind blown. So cool. So awesome. All right. I already did that. So supplementary angles of a triangle. This is really basic, but you need to know. It's really all the stuff we're doing today is basic and stuff you probably known since middle school, but I'm taking it to a whole nother level. All right, so the three angles here, they all add up to 180 degrees, and we know they add up to 180 degrees, but we can actually prove it. One of the ways we do it, we take a line parallel to the base through the apex, so this opposite side here, this opposite vertex. And then we notice that these lines are parallel by construction. Then we know the alternate interior angles. So this angle 2 is the same as this angle 2 up here because they're alternate interior. This angle 1 is alternate interior to this angle 1 here. And then we know that these three angles, angles 1, 2, and 3, have to add up to a straight line. And so the sum of the angles, angles 1, 2, and 3, add up to 180. So the same angles on the triangle 1, 2, and 3 also add up to 180. So if we want to like show that with an actual example, we basically draw the line up here. And then we know the alternate interior to 33 is going to be 33. The alternate interior to the 90 down here is another 90. And then all three of these add up to 180. So 33 and 57 is 90. Another 90, of course, is 180 degrees. So kind of cool. Sum of the interior angles has to be equal to, it's all going to add up to 180 degrees, which is the straight line. Kind of fun. All right, so you can also see through this widget here with GeoGebra. So I constructed this line CD to be parallel to AB. So as I move the point B, it's going to move CD, so that's always parallel. And anytime I stop here, you'll notice that the sum of these three angles here are always 180 because it's, you know, a straight line. And 68.11 is the same as 68.11. Same, and those are always alternate interior angles. So as one of them changes, so does the other, which is pretty fascinating. And at any time, no matter what shape of a funky, weird triangle I want to create, whoa, the sum of the interior angles is always going to be equal to 180 degrees. Not what I was trying to do. Okay, pretty cool though. All right, some of the exterior angles. All right, so the interior angles are in green. The exterior angles are in blue here. They're just going to be the angles on the exterior of the triangle. But you're going to be a little careful on some of them on the homework. I'll show you that. But anyway, it's going to be adding up to more. And if we want to figure out exactly what they add up to, instead of 180, we can actually just use this example. So the supplement of 57 is going to be 123. The supplement of 33 is 147. And the supplement of 90 is 90. So I can add all those together. And when I do, I find out the sum of the exterior angles, if you have a calculator, you can do it, is 360 degrees, which is really stinking cool. And there's actually some proofs that can show you why it's 360 degrees, but we'll save that for tomorrow. All right, so let's go ahead and get started on the homework. So a little bit longer on the lecture. I apologize. I'm introducing a lot of new stuff to you, but pretty much this is the only new stuff you're going to need for the whole week. So the assignments we're doing, and we're only doing 3 assignments this week, which is pretty awesome. All right, so on number 1, on this one, we want to identify the shape by the sides, the angles, and the shape itself. Okay, so basically you're going to pick one from each one of these columns. So the first thing, the sides, we've got 2 10s here, so this is actually going to be isosceles. And then the angles, we have a right angle, so it's an isosceles right. It's got 3 sides, so it's a triangle. So we call this an isosceles right triangle. You can abbreviate it like I've done here, use symbols, I don't really care. And as you go, you can cross these out. Now notice, they're not going to line up going across. These are just, if you notice going down here, they're in alphabetical order. Same as these are in alphabetical order, and these are in alphabetical order. So that's just how I organized it. So on this one, isosceles, right, and triangle. And don't worry, it doesn't match up going across. So no big deal. All right, number 2. So I already did the isosceles right triangle. On this one, how many sides we have? 1. Well, we got 5 points, but there's 2 on each point. So this is a decagon. Remember, we actually talked about this one. Is it regular or irregular? Well, again, we're not looking at the sides are all the same. It's that the angles are all the same. They're not all the same. So this is irregular. Our angles on this one, this one is concave because it's caved in. And then the shape is a decagon. So this is a irregular concave decagon. You could just do cave if you want. Cave dec. However you want to abbreviate it. Just trying to save you some time. 1, 2, 3, 4, 5. 5 sides. So it's a pentagon. It's not a regular pentagon because not all the angles are the same. And it's not caved in, so it's convex. So this is going to be an irregular convex pentagon. All right, on this one, all the sides are different, so that's going to be scalene. We do have our obtuse angle, so it's a scalene obtuse triangle, so it's pretty simple. And then on number 5, 1, 2, 3, 4, 5, 6, 6 sides, so this is a hexagon, and all the angles are the same. So this would be a regular convex hexagon. Yep, got it. So reg, vex, hex. There you go. All right, 6, 1, 2, 3, 4, quadrilateral. All the angles are not the same. All the sides are not the same either, of course. So this one's going to be irregular convex, because it's not caved in, and quadrilateral. So irregular, convex, quadrilateral. Okay, cool. All right, number 10. So on this one, we want to solve for the missing angle. These are all interior angles. They're all green, okay? I'm trying to help you there, which means they add up to 180 degrees. So add these two together, subtract it from 180, and you'll get your missing angle, which I didn't actually program. So let me grab my calculator. Oh, there it is. And I'm going to do this. All right, so we have 65 plus 86 as 151, then we're going to subtract that from 180, which leaves us with 29. So the missing angle here is going to be 29 degrees. All right, now this is different because it's blue. See, green, blue. That's a hint. This is an exterior angle where these two are interior angles. So we can solve for the missing interior angle and then just find the supplement of it. Probably the easiest way to do it. And doing that, we'll discover a theorem, actually. So 30 and 100, so 130 minus 180, because remember those all add up to 180, the sum of the interior angles, is going to leave us with 50. And then if this is 50, the supplement of 50 is 130, which should sound familiar because that's really just the sum of these two angles over here. And so yeah, it's really, you could just add those two together to find the exterior angle that's adjacent to it, I guess you could say. So yeah, that's triangle exterior angles theorem, I believe. Yeah, it's got a name. All right, number 12. So on this one, we have a triangle. We have all three of the angles are A, 2A, and 2A. So this is isosceles. We do know these two are equal to each other. But if I set up the equation 2A is equal to 2A, then what do? Like divide by 2, and then I end up with A is equal to A. Reflexive property, right? Okay, so that's not very helpful. So instead, what I need to do is add them all together. And you know we have a triangle here, which means they're all going to add up to 180 degrees. They're all interior angles. So the 5 A's together adds up to 180. And then I divide everything by 5, which leaves me with A is equal to 36. So now I know that A is equal to 36. And you can fill it in here and cross it out. What's 2A? Well, 2A is 2 times that, which is going to be 72. So all the angles I have here are 72, 72, and 36. And if I added those three together, sure enough, they would be equal to 180 degrees. So we know we did it right. All right, 17. On this one, we've got two interior angles, then some funkiness going on down here. Well, just first focus on the triangle. We've done some problems like this before. So we got the triangle. We know they all add to 180. So add these together, 65. The supplement of 65, I guess I'll show it here. So 180 minus 65 is going to be equal to 115. So the missing angle here is 115. All right, got it. And then x is vertical to that, right? So it has to be 115 as well. So that's not too bad. You can cross that answer out. You can also just write it underneath it, I'm sure, because you got it. It disappeared. All right, so x is equal to 115. You get the idea. Has to be perfect. That's going to bug me. All right, anyway, and then once we have this angle here is 115, we can find the missing angle y, which is its supplement, which is going to be, I believe, 65. Does a 65 sound familiar? It should, because that was the same as the sum of these two angles up here. Again, that same weird theorem coming in. So once you find the supplement, it's the supplement of itself. So it's kind of cool. You can memorize that if you want. If you don't, I don't care. All right, so on this one, we have an interior angle of 73. But 63 is interesting because it looks like an exterior angle, but it's actually an interior angle because it's vertical to this one. Isn't that weird? So these two are vertical, so x is equal to 63. So the exterior angle is actually this angle right here. So these two are exterior angles. This is an interior angle, and this is technically an interior angle as well. Head scratcher, but it is. It's just being shown on the outside of the triangle. Anyway, don't let that bother you too much, but do be careful. There's a lot of mistakes I see here on the test, so don't go too fast. This is truly an exterior because it's not vertical to the inside, and this is an interior angle, right? So we have 63, 73, add those together is 136. They all add up to 180. So I'm going to do 180 minus 180 minus 136, which is going to leave me with, I believe, 44. Yeah, 44. All right, so the missing interior angle Y is 44, and then the supplement of that is right here, right? It's going to be that 136. Again, it's the sum of these two non-adjacent sides, interior angles. Okay, cool. All right, number 22. So we're looking at the sum of the interior angles of a polygon. This one's really, really important. We're going to go through it together. Really cool discovery thing that we get to do. So when we have three sides, we call, which is number 22, it has three sides. It's called a triangle, polygon name. Number side's 3. How many triangles are in a triangle? That's not a trick question. It's just 1. Okay, and then so what's the sum of the interior angles? Well, if you remember, we were able to move this one up here, and then this thing was the same as that one, this one was the same as that one. So all the angles added up to 180 degrees. All right, because we had one triangle. So sum of the interior angles is going to be 180. And we're going to be filling in this chart as we go. All right, so number 22, I guess. So now it has 4 sides. And so that is now a quadrilateral, has 4 sides. How many triangles? So what we're going to do is essentially we're going to start out in one point, which I'm starting out this point here, and then from this point I want to connect a line to all the opposite points. So if we're in class, we're going to be doing this with a ruler. You can just draw it, sketch it, or whatever. Just do it rough, or if you print it out, you can use a ruler at home. But how many triangles would we form? Well, the first one would form one triangle and then a second triangle over here. So there's 2 triangles on the inside, and these are all interior angles. So all 3 of these angles here are going to add up to 180. Then all 3 of these angles here, I'm just marking them on the same one, are also going to add up to 180. So together they're going to add up to 360 degrees, which is kind of cool. So how many triangles we have in a quadrilateral? Well, we have 2 interior triangles, and the sum of the interior angles are 2 times those 180 for each one, right? All right, spoiler. All right, the next one has 5 sides, and so we call this a pentagon. It has 5 sides. There are 3 triangles, so 1, 2, 3. So that would be 3 triangles, and each one of those triangles, each one of these angles are going to add some of these 3 angles here are 180. The sum of the next 2, I'll change colors, how about that? Those are going to add up to 180, and then the sum of these interior angles here are also going to add up to 180. So 180 plus 180 plus 180 altogether is 540 degrees. All right, cool, moving on. And then 6 sides would be 4 triangles. So it's a hexagon, 4 triangles, and then each one of these 1, 2, 3, 4, and there's 184 times, which is going to be 720. And you probably notice a pattern, hopefully, at this point. Good mathematicians pick up on patterns, and then we write conjectures, and that's pretty much math. All right, 7 sides would be 1, 2, 3, 4, 5. So it's called a heptagon or a septagon, whichever one we call it. It's got 5 sides, and then we just add another 180, right? So 180 plus 180 plus 180 plus 180. Also, the number of the triangles is just increasing by 1 each time, right? So the next one should have 6, and then after that 7, 8, 9, 10, and then we add another 180 to it, which would give us 900 and 1080, right? And after a septagon, we would have an octagon, etc., etc. Okay, so spoilers, but that's pretty much what's going on here, because every time the number of triangles is always going to be 2 less than the number of sides, and then we take 2 less than the number of sides times the 180, which will give us our formula, which we'll do that in just a second. So 8 is going to be obviously an octagon. There are 6 triangles to it, and 6 times 180 is going to be 180. All right, so what about an n-gon? Well, an n-gon has n sides, where n is just some variable. So it's not well defined in this case, it's just a variable. All right, so how many sides do we have? Well, we have n sides. How many triangles would we have? Well, if we notice the relationship between the number of sides and the number of triangles, it's always 2 less. So 3 minus 2 is 1, 4 minus 2 is 2, 5 goes 3. So it's always 2 less. So the number of triangles you have in n-gon is going to be n minus 2. So whatever the number of sides was n sides, we'll have n minus 2 n minus 2 triangles. Now the reason for that is because the first two sides that we have don't form a triangle. It's not till you get to the next side after that, or this next one down here, that actually will form the triangle, which is kind of cool. So it's always n minus 2. All right, so what's the sum of the interior angles? Well, if we have n minus 2 triangles and each one of those is 180 degrees, the formula would be n minus 2 times 180. So this is the general formula for any polygon where you have n sides. And by the way, we just call this an n-gon. So the sum of the interior angles of any polygon is n minus 2 times 180, which is beautiful. All right, so what if we had 23 sides? Well, you don't have to draw the triangles on this one. You just plug it into the formula. So 23 sides minus 2 would be 21 triangles. And then 21 times 180, put it in the calculator. I'll do that real quick. 21 times 180, which will give us 3,780 degrees. So the sum of all 23 of these angles is going to be 3,780 degrees. Kind of cool, all coming from this formula that we discovered. All right, number 26, this has 1, 2, 3, 4, 5, 6, 7, 8, 8 sides. It's, of course, like a stop sign, so it's octagon. So 8 minus 2 is going to be 6, so 6 triangles. And we can actually see those here. So the first triangle, here's the second one, and the third one, and the fourth one. And then when we draw our last line here, it's actually going to make the last two here. So there's 6 triangles altogether times 180, which is going to be 1080. All right, so the sum of the interior angles of regular polygons using the formula. If you notice, 32 is the exact same as 26. So those two groups of problems are the exact same problems. They're just asking a separate answer. I did that to help you out. So if you remember on this one, we had the sum of the interior angles was 1080. So all these 8 interior angles are going to add up to 1080. So if the question is, what is one of those angles? Well, if we think about it, there's 8 of them altogether, right? And they all are the same, and they add up to 1080. So it's like we're doing 8 x's is equal to 1080. So if we want to figure out what one of those x's are, we just divide the total of them divided by the number that we had, which gives us x is equal to a good question. So 1080 divided by 8, which is equal to 135 degrees. All right, try that part again. I'll just lift my pen. All right, so 135 degrees, that's what each one of the interior angles, and all of them are going to be 135 if it's a regular octagon. So if one of the interior angles is 135, what's one of the exterior angles? Well, its supplement, which would be 45 degrees. All right, 27, we said, if you remember, if we go, oh, no, this is a different one. So on 27, we got 5 sides, so 5 minus 2 would be 3. 3 times 180 is 540. That needs to be fixed. I did that wrong, and I forgot to update it. All right, so it would be 540 degrees. So the sum of the interior angles is 540 on this one. So what's one of them going to be? Well, there's 5 sides altogether. 540 divided by 5 would give us 108. Yeah. And if one of them is 108, then what's one of the exterior angles? So the supplement of that, which would be 72 degrees. All right, cool. Good to go. All right, so that's it for today. You should be able to get the rest of the assignment done. Sorry it went a little bit long. And I'll do the next video for tomorrow. And pretty much the whole rest of the week, we're doing the same stuff, just talking about polygons. So I'll see you later, and hope you have a good day.